Hi, I'm Mike Coyle, and you're watching Inside Exploration. Today I'm here with a special guest, Jim Renaud. He is the owner of Renaud Geological Consulting, and he's been working for RJK Explorations in plotting their indicator minerals, where RJK has been exploring for the source of the 800-carat Nipissing diamond. Jim, thanks so much for taking the time to go over this with us and explain how this process works.
Hey, hi, Mike. Thanks very much for having me, and look forward to talking about this.
Yeah, so before we get started in the interview, why don't you go ahead and tell us a little bit about yourself and what you do and how you came to start working with RJK Exploration.
Sure. So my name is Dr. Jim Renaud. I'm president and director of Renaud Geological Consulting. I'm a graduate of Western University. In 2005, I founded Renaud Geological Consulting with my wife, Natalie, who's also a geologist. At that time, we purchased an electron microprobe from Caltech University, which sits behind me, and entered into the exploration world by analyzing diamond indicator minerals. Over the years, we expanded our business into other areas, including field programs, and worked on a diverse range of deposit types, from precious and base metals to uranium, iron ore, and rare earth elements. However, a large percentage of our lab business for well over 15 years has been analyzing diamond indicator minerals. I've also done many related petrographic rock studies for mostly junior companies and for many that have gone on to become developed mines. So looking back, I've analyzed probably tens of thousands of indicator minerals. And to this day, we continue to work with junior exploration companies and prospectors supporting their exploration programs.
Excellent. So you're going to give us a little bit of a presentation here and show us what it is that you do on a day-to-day. So where I'm just going to go ahead and let you go share your screen and give that presentation and kind of explain to people your process.
All right. So the mineral chemical data provided to me by RJK. The mineral chemistry was done by CFM Minerals out west. And RJK has asked me to present the data on various diamond plots to characterize the different indicator minerals. So we'll start with the garnet plots, and I'll begin with the calcium versus chrome plot, and then we'll look at the calcium versus titanium and the calcium versus sodium. So this here is an all-encompassing graph of all the data points from RJK, from their various sample sites here. What I want to do is just kind of go through this diagram and explain what the different fields mean. So we'll start with the axes. So calcium and weight percent is plotted on the X, and chrome Cr2O3 weight percent is plotted on the Y-axis. This line here is called the G9, G10 divide. It intersects the X-axis at about 3.3 weight percent CaO. And this line represents the calcium saturation characteristics of Harzburgitic and Lersiditic rocks. The G9 field contains chrome pyropes derived from the Lersiditic mantle, and they are the most abundant garnet type recovered in exploration programs. And then the G10 are Harzburgitic, and Gurney correlated that 85% of prototypic garnet inclusions in diamonds were calcium poor and chrome rich Harzburgitic pyropes, and that's what this field represents. This line here is the diamond graphite stability line, and it was developed by Gruder and Sweeney in 2000. So anything falling above that line is considered to be within the diamond stability field. Down here in the G5 box, these tend to be low to moderate chrome garnets. They tend to have a bit more enrichment in sodium and titanium. And then these over here in the G1 tend to be part of the low chrome suite of garnets. And these here are the eclogetic garnets down here that plot along the bottom. So what we'll do is we'll look at each graph plotted separately with their own data points. So here we have the Paradis Pond data set, and you can see a nice cluster of points plotting within the G9 field. Again, common to see in most kimberlites. But what's interesting is this nice cluster of G10s here, and a nice array of points falling above that diamond stability line, falling in that G10 diamond stability field. There's some points in here in the G5 also, some eclogetic points along the bottom, which we plotted on other graphs. Some of them have a slightly elevated chrome content. And the one thing that stands out on this graph for sure are these 3 points here to the right. These are mantle-derived garnets with elevated calcium and chrome, and these tend to occur in xenolithic fragments. So it's good to see this cluster of points too. Now for the sample PP 2009, again we see a cluster of points in the G9 field. But if we compare it to this one on the left, you can see that these points here have shifted a bit to the right, and that might imply that a different part of the mantle was sampled, or this could be another phase of the kimberlite. So there's a couple of different explanations you can use for that shift. But you can see that they've moved more towards a slightly higher calcium component. And then again, some nice points here in the G10 field, and a standalone point up here, well above the diamond stability field, stability line, approaching 12 weight percent Cr2O3. Now for the PP 2003-04 sample, again, a cluster of points in the G9 field. You can see that the line has a bit more of a diagonal trend to it, again, suggesting possibly a different part of the mantle sampled, or perhaps some sort of metasomatic reactions which have caused a different mineral chemical signature in these garnets. Some more points here in the G10 field, which is great to see, and points down here in the eclogetic garnet field. The KON sample data set, again, cluster of points in the G9 field, common to see in many of the global kimberlites, and common to see in a lot of the exploration programs. But not so common are these G10, and it's great to see these clusters of G10 garnets in these sample suites. A cluster of 3 points up here, which may represent a cluster of garnets from the same mantle nodule type thing that have similar chemistries. Now, the eclogetic garnets were plotted in terms of calcium titanium, and it's what you want to see is this increasing trend of titanium in these eclogetic garnets. It shows elevated titanium, indicative of kind of elevated pressures, substitution implying a deeper mantle source for these eclogetic garnets. This graph here represents calcium sodium plot. This is of the Paradis Pond, and first thing we notice is this horizontal line which cuts across the graph at 0.07 weight percent sodium, and it's believed that anything falling above this horizontal line defines a more prospective eclogetic garnet composition. And these eclogetic nodules are possibly diamond perspective. So these are great to see, these elevated sodium contents. Now, when we look at the chromite graphs, we'll look at Paradis Pond first. This is a titanium versus chrome plot. Again, various fields here on this graph. The most important being this diamond inclusion field up here. And then in here we have the overlap field, and then field unique to kimberlites and lamproites, and the non-kimberlite field down here. So with this RJK data, you can see a lot of points within this overlap field, and a lot of the points are elevated in chrome, and a really nice diamond inclusion chromite up here, and a cluster of points here in this unique field to kimberlites and lamproites. So it's good to see these points. And then these two down here might be derived from a more crustal source. Now the KON graph is a little bit different. It tends to show this horizontal trend of the data points. I don't particularly have an explanation for this, other than this might represent a core to rim zoning of the chromites. So this might represent a deeper mantle source, and these might represent the rinds or the rims on those grains as they ascended through the mantle into the crust. So these might be reaction rims. We'll have a quick look at the ilmenite graphs. First of all, the ilmenite graphs are plotted in terms of magnesium titanium. There's two parabolic lines here, or arc-shaped lines, that are represented on this graph. This top line here, which intersects the x-axis at lower magnesium contents. This line implies lower magnesium contents, representing the boundary between more kimberlitic ilmenites to the right and non-kimberlitic sources to the left. And this other line, the second line here, is the bounding reference line of kimberlitic ilmenite composition. So anything falling to the right of this line is considered prospective. So we notice a bunch of points over here to the far left, possibly a crustal source, maybe from a dike or something like that, whereas these here are plotting within the kimberlite field. The same points are often plotted on a magnesium chrome plot. And what's interesting about the magnesium chrome plot is that Haggerty in 1991 defined a parabolic shape to this graph, in which points on the left side of the parabola would be less prospective for diamonds, as opposed to the right side of the parabola, which would be more diamond prospective. And looking at the RJK points here from Paradis Pond, there's definitely a trend here on the right side of that parabola. And these points down here are those crustal ilmenites. So looking at the KON graphs, again, those two arcuate lines, it's one point here falling to the left in the non-kimberlitic field, whereas these points here are plotting to the right within the kimberlite field with elevated magnesium and titanium, and falling within the diamond stability field of this graph. Now looking at the magnesium chrome plot of that same graph and thinking about that parabola, again, nothing happening on that left side of the parabola, but we definitely have some grains here forming that right side of the parabola, which is the side that you want to see your grains on. In terms of the Clinopyroxene graphs, Clinopyroxene data is generally plotted on a sodium versus chrome plot. Some points, as you note here, are plotted close to the x-axis, and the chrome dioxides, they define, you can see a linear cluster or trend with increasing sodium and increasing chrome. And this trend to increasing sodium and chrome defines an increasing substitution of the ureite molecule within the diopside omphacite structure of the clinopyroxene. And that substitution is considered to be a function of increasing pressure, suggesting derivation of these grains from a deeper mantle source in the diamond-bearing stability field. So it's great to see these elevated sodium and elevated chrome grains. Just looking at some of the points on this graph, you can see that some of them form these pairs. One possible interpretation here is that, again, this might be quarter rim zoning, so a more sodium-rich core, and then maybe a reaction rim or something like that, forming the rind. So again, a core and a rim possibly, and a core and a rim. In terms of the KON sample suite, again, no points down here on that x-axis, and they're all forming that nice trend of increasing sodium, increasing chrome, and some pretty spectacular sodium chrome compositions with like 2.5% sodium and 3.5% chrome. So if we consider the RJK data suite and we think about other diamond mines and just globally some thoughts on mineral chemistry, we'll start here with this plot from the Victor mine. Here's the reference for the paper if you're interested. Interestingly, they have eclogetic garnets along the bottom, which RJK also has. They have the points falling within the Lurslite field, which RJK has. The one thing this graph does not have is the points within the G10 field, which RJK does have. And it's great to see the indicators within that G10 field. Victor also has some pretty extraordinary compositions of garnets with very high calcium and extremely high chrome contents. These tend to be green garnets and that sort of thing, which stand out from the dark purple garnets you're used to seeing in the G10 field. Here's a graph from South Africa, from the Karowe diamond mine. Here's our calcium chrome plot again, and you can see a nice cluster of eclogetic garnet points along the bottom, some with a bit of chrome in them, and then not so much in the Lurslite component, but they do have quite a number in the Harzburgitic component. And here's that diamond graphite stability field line, and you can see a lot of data points falling along or above that line. And one extraordinary point up here around over 14 weight % chrome, subcalcic garnet, falling on the 7 gigapascal line, which is incredibly deep. So the RJK grains, if you think back to the calcium chrome plots, have points within the Lurslite trend, and they also have a whole lot of points in this Harzburgitic G10 field, sharing some similarities to this particular mine. And then in a global context, global data set of garnet inclusions within diamonds. So you can see that in terms of the Lurslite garnets, there are not many G9s that occur as inclusions within diamonds. The majority of the population of garnets within diamonds are G10s, and RJK has quite a number of G10s, which is very encouraging. In terms of summary, the RJK Kimberlite has very interesting mineral chemistry. It's comparable to a number of different mines in the world, and has many similarities to this global database of garnet inclusions and diamonds. They have great looking CPXs. They have some diamond inclusion chromites. Their ilmenites look great, and I think it's definitely a project to be excited about, and with a lot of upside potential and for positive news. So really looking forward to continuing to work with RJK.
Well, this has been extremely informative, and I appreciate you taking the time to kind of go over this with us. So we'll get this out to people, and maybe they'll have a better understanding of what's going on with RJK. So thank you very much, Jim. I appreciate your time.
Well, thank you very much. Take care.